Hey, welcome to the Explainer. In any competition, whether it's a business deal or just a simple game, what if there was one single perfect move? A move that gives you the best possible outcome no matter what your opponent does. Well, today, we're diving into a core concept from game theory that helps us find exactly that.
Here's our game plan for today. First, we'll get our heads around what makes a game strategic. Then, we'll learn the lingo before we go hunting for the saddle point. That's our optimal move. We'll see it work in a real example, test what we've learned with a little puzzle, and then wrap it all up with the one big takeaway you can use anywhere.
So, when you hear game theory, you probably think of things like chess or poker, right? And you're not wrong, but its reach is so much broader. At its heart, it's the formal study of decision-making, where the outcome of your choice depends entirely on the choices of others.
Think about it like this. Imagine two businesses are launching a really similar product at the exact same time. Well, one company's pricing strategy is going to directly impact the other's sales and profits. Game theory gives us a framework to analyze all these moves and countermoves, basically turning a complex business problem into a competitive game we can actually solve.
Okay, to find a winning strategy, first we need to speak the language of the game. Let's quickly go over a few essential terms that are going to unlock how all of this works.
First up, the player. This is just any decision maker in the game. A player could be a company setting prices, a country negotiating a treaty, or, even you, trying to figure out the best way to ask for a raise.
Next is a pure strategy, which is a very straightforward game plan. It means a player decides on one specific action and just sticks with it every single time. Think of someone playing rock, paper, scissors who, for some reason, always chooses rock. It's a consistent and totally predictable plan.
This brings us to a specific type of game, a two-person zero-sum game. It's basically a closed system. If I win $10, you must have lost $10. The net change zero, because one person's gain is perfectly balanced by the other's loss. A lot of classic competitive scenarios can be looked at this way.
All right, now we get to the core of it. How do we find the single best move in these games? This is where we uncover the secret to a stable, optimal solution, something called the saddle point.
A saddle point is this special value in our game that represents an equilibrium. From this position, neither player has any reason to just change their strategy on their own. Why? Because if they do and their opponent doesn't, they'll end up worse off. It's kind of like the point of no regrets in the game.
What's really amazing is that there's a single, elegant rule to check if a saddle point even exists. We just need to see if two values are equal, the Maximin and the minimax. Now, it sounds complex, but it's a very clear test that represents each player's best defensive strategy.
Let's walk through how to do it. For player A, the row player, we first find the minimum, or worst possible outcome, in each of their rows. Then they choose the best of those worst outcomes, the maximum of the minimums, or Maximin. Now for player B, the column player, we find the biggest payoff they could possibly lose in each column. Then they choose the move that minimizes that maximum loss, the minimum of the maximums, or minimax. If those two values match, boom, that's our saddle point.
Theory is one thing, but really, the best way to understand this is to just see it in action. So let's apply these steps to an example and solve for a saddle point right now.
Here's our game board. Player A can choose one of three strategies, A1, A2, or A3. Player B can also choose between B1, B2, and B3. The numbers in the grid, that's the payoff that player A gets for each combination of choices. So for instance, if A plays A3 and B plays B2, A gets 5.
This really shows you the tension of the game. Player A looks at each of their rows and prepares for the worst, aiming to maximize their minimum gain. That's their Maximin strategy. Player B does the opposite. They look at each column, see the best player A could possibly do, and then choose the move that minimizes that maximum loss, their minimax strategy.
Okay, let's apply our procedure. First, let's find the minimum of each row. For row A1, the minimum is 1. For A2, it's -4. For A3, it's -1. Now for the columns. The maximum of column B1 is 1. For B2, it's 5. And for B3, it's 1.
All right, let's find our two key values. The Maximin for player A is the maximum of those row minimums we just found. So the maximum of 1, -4, and -1 is 1. The minimax for player B is the minimum of the column maximums. So the minimum of 1, 5, and 1 is also 1. Look at that, they're equal.
Because max and min equals min-max, we have found a saddle point, and the value of that point tells us the value of the game. In this case, it's 1. This means if both players play optimally, player A will always gain 1.
So what does this all mean? We've found the best pure strategy for both sides. To guarantee a gain of at least 1, player A should always play strategy A1. To make sure they lose no more than 1, player B should play strategy B1 or B3. This is the stable, logical outcome of the game.
Okay, let's put this knowledge to the test. What happens when a payoff matrix has some unknown variables? Let's try to solve a little puzzle.
Take a look at this matrix. We've got 2 unknown values here, P and Q. But we have one critical piece of information. We are told that the number 7 is the saddle point of this game.
So, here's the question. Based on the definition of a saddle point, what conditions must P and Q meet for 7 to be our stable solution? This forces us to work backward and really test our understanding of the whole concept.
The logic flows directly from the definition. Remember, a saddle point has to be the minimum of its row. So for 7 to be the minimum in row A2, Q has to be greater than or equal to 7. It also must be the maximum of its column. So for 7 to be the maximum in column B1, P has to be less than or equal to 7. That's really all there is to it.
Okay, let's recap the optimal takeaway from all of this and why this idea of a stable solution is such a powerful concept.
Basically, you now have a new tool for looking at competitive situations. By finding a saddle point, you can identify a stable outcome where neither side has an immediate reason to change their plan. That Maximin equals minimax rule is your key to unlocking both the value of the game and the single best, most defensible strategy for each player.
So think about it. Where in your own world do you see situations where 2 sides have settled on a strategy just because any other move would make them worse off? It's a fascinating lens to view competition through. Thanks for joining this explainer,